The broadcast is now starting. All attendees are in listen-only mode.
Hello and welcome to our Advanced Methods for Compaction Quality Control webinar, which is brought to you by NACOE, the National Asset Centre of Excellence, and the Australian Road Research Board. My name is Rosemary Patterson and I'll be your moderator today. We will be running 50 minutes for 10 minutes for questions, and we'd love to hear from our audience, so please engage with us through the questions box. We'll take some questions along the way, but we also have a dedicated questions spot. Any questions that we don't get to, we'll respond to by email later, and the session will be recorded. Our presenters today are Dr. Jeffrey Lee, Dr. Bert Look, and Dr. David Lacey. And Dr. Jeffrey Lee has 18 years engineering experience with a focus on pavement and geotechnical engineering. He is currently a principal pavement engineer at the Australian Road Research Board, responsible for the delivery and managing research projects under the National Asset Centre of Excellence, NACOE program. Dr. Bert Look has 35 years professional engineering experience with over 32 years specialisation in geotechnics. Bert is 2014's Queensland Professional Engineer of the Year, and Bert has published 3 geotechnical engineering books and over 70 technical publications. Dr. David Lacey has degrees in both geophysics and civil engineering. His part-time PhD candidature investigated appropriate testing methods to assess in situ material parameters of residual soil profiles. David was 2016 Engineers Australia Young Professional Engineer of the Year. So welcome Jeffrey, Bert and David. And before we get started, we wanted to find out about our audience. So I'll launch the poll and welcome to you all. How are you all?
Very well, thank you.
Excellent, thank you.
Great to be here, thanks.
Awesome. So I've just launched the poll which says, which of the following best describes you? And our audience can click on one of the answers. Some people may have more than one answer. And while we're voting, I might ask Bert, who do you think might be the largest group in our audience?
I believe it comes from mainly consultant, but there are a significant amount of road authorities and possible councils in there. That remains to be seen, but I think that's where we'll have the main audience, and to some extent the presentation has been geared towards that audience. Apologies to the contractors out there, but I guess one has to pick the main areas of emphasis, and I think that's where we'll sit at this point in time. I stand to be corrected after the poll.
Awesome. Well, I've closed the poll and I'm going to share it with the audience, and it looks like you've designed your presentation correctly. So we've got consultants, 63%, State Road Authority people, 25%, we've got 8% contractors, and we've got 4% from ARB. And I know that you've got lots of information for each one of those groups. So let's get started.
Okay, thanks, Rosemary. Again, my name is Jeffrey Lee from ARRB, and I'll be starting the webinar. As you can see on the screen, we anticipate this webinar series to be in 3 parts. In today's presentation, which is part 1 of the webinar, we're going to talk about give audience an overview of these topics. For example, like the basic of densities, and the different rationale for some of the equipment that will be presented in these studies, and we'll provide some initial findings as well. We are expecting to have the part 2 of this webinar will be in later part of this year, and things will be getting more exciting from my point of view, where we'll present some data from different test site and some correlation with what we call standard practice, and and we'll discuss a bit more about the time, reliability, and the usefulness of the data. And the last part, part 3 will be more like rolling out some of these procedures. How can we be putting it in our specifications? How can we use it in the construction site, and the different advantage and limitations? So this sort of set the frame for our webinar series. So if you are here on the part 1, make sure you don't miss part 2 and part 3. And so this webinar is actually the outcome of one of the projects that I'm leading here, and is sponsored by the National Asset Centre of Excellency, which is an initiative of the Queensland Department of Transport and Main Roads, as well as ARP. The title of this project is P60, which is under the pavement discipline area in the research program. The title is Best Practice in Compaction Quality Assurance for Subgrade Materials. So again, my name is Jeffrey, and I'm Principal Pavement Engineer here at ARP. And together with Siva, who is the TMR project managers on this project, and as well as Dr. Bert Look and Dr. David Lace from Foundation Specialist Groups, which we've been working for the last 2 years. And if you want to find out a bit more about the NACOE program, what exciting research projects we are doing, some of the technical publications, or how information on how industry can be involved, please follow the web link here, as shown on the slide. So in short, right, the aim of this NACOE P60 project is to modernize the testing procedure for compaction quality assurance. Some of the background which Bert will be elaborate more would be like, conventionally, this compaction quality assurance has been relying on density measurements, but over the last 2 decades, there are other new methods that has become available, and some of the jurisdictions, like in US, they actually have been rolling it out. So hence the reason for this research project. And one of the highlights is that a lot of these alternative methods actually takes less time to do. The results is available in much shorter period of time, so we don't have to wait for long, and it's a measure of the in situ stiffness. With that, I think that's enough of an intro, and I'll pass it on to Bert for the. Yep.
Thank you, Jeffrey. Okay, here we go. I guess the first deep and meaningful question of why we do what we do. Why should we be looking at these test methods? After all, we have been going merrily along the road, so to speak, with our density testing. It has worked well, and it has served its purpose. But is it the best practice that we should be focusing now? And we need to be careful here of, yes, it's good, yes, it's been doing a good job, but this is the best approach currently. And often the question becomes, why do we do what we do? And it's a strange sort of answer. It's because that's the way we do it. And we need to be careful with that answer, because times change, the knowledge changes, and the background for lots of things change. And you will find, and as part of this presentation, I need to get you up to speed in fact that density, the reasons why we do it, it has an interesting background, and I will present some of that, but actually it raises a lot of question of, is that the best approach with current technology? Okay, you'll see a few light-hearted slides in between. I guess it's all part of my enjoyment of doing what I do. We got to just relax a little bit. While it's all technical, hopefully you'll get a bit of fun out of it as well. So moving on, and Jeffrey sort of introduced 4 of these aspects in a summary fashion initially, but what we need to understand now is a bit more on some of these issues. Now, it was mentioned about it being a lag indicator, and that's a key aspect, but why is it a lag indicator? sorry, we need to just be careful on that. The reason I'll expose shortly, but that's one of the key things, as well as when we do the CBR test, that is also, can also be a lag indicator to some extent. Now, when a contractor, for instance, does the pavement, they do it with the best intention and think the result is okay, and often push fill above that another layer, 2 or 3 layers, because the results take a while to come through. And then, of course, if it doesn't come through, then the contractual dispute starts. Now, I guess they believe they have done a good job, and you back yourself, because without that, equipment is on standby, and that could be significant cost. But if one finds a result but it's not acceptable, to remove that other material and come back down, and we are talking about sometimes 25K upwards. 50K wouldn't be unreasonable, depends on how much space you have and whether they use equipment elsewhere and how much lifts they have pushed up above. So we're talking about a significant cost as well as time for when we have a lag indicator. The other parameter is about the density oversize correction. And you'd see there where it is mentioned 22% of 235 samples examined. Did this a couple of years ago, and it was interesting for a project that was a good project, done, completed, passed, etc. That 22% of samples that were part of the compaction QA should not have been a part of it. And that's interesting, because it means that we have testing procedures and certain things about correction for oversize, and it's not been applied across industry. That raises a lot of questions here about our QA. It doesn't mean it would have been a failed sample. I'm not going there. I'm just saying whether that sample was appropriate or tested correctly. Because if there's a certain oversize, we should not be using that unless we correct for it or certainly not use for it. And yet that's not happening across industry. And that's 22% of a project that was, shall we say, successful. So that's something that happens in the background, and one wonders, why did the lab not do the correct thing? I'm from one of those who think that people do try to do the correct things. It's a question of sometimes, in this case, a commercial reality. To do the correction does have a cost. And who pays for that? Especially when you want a job on assuming that you'd have the least to do. That's how jobs are won and lost. And if you have to do a correction, it comes at a cost. Do you now barter for that cost, or simply just give the results and hope the users of those results understand, well, it wasn't quite applicable if they looked at something else, such as a gradient. So it could be as simple as that. Just moving on to the other parameter now, which is strength and modulus. That is a very variable parameter, especially when one has a correlation attached. We use E equal to 10 CBR as a typical correlation, yet it could be 20 or it could be 5 times CBR. That's a very broad brush of our correlation. And to think that's the basis of our design and saying, oh, could be 100% off, doesn't thrill one with a lot of confidence of doing what we do. To make it more difficult is that we assume density is related to modulus, i.e., we have a high density, therefore we have a high modulus. That's a big assumption. Just keep that in mind, and I will run through that aspect shortly. Okay, so compaction quality control, we did complete a state of industry in 2017, which provided a bit of a technical aspect to it, and that was completed last year. In this past financial year, up this, we have completed some field trials, and we should be presenting the results of that shortly, hopefully before the end of the year. Jeffrey's nodding, so look out for part 2 of that. And the 2017 summary is complete. From a technical point of view, you may wish to add something to that, Jeffrey. What about from a information reporting point of view?
So in 2017, we done a comprehensive literature review, and it should be up on the NACOE website, the web link that I showed earlier. So, make sure you go and check it out often.
So a lot of the descriptions of test results and everything are critiqued and described in that literature review. So a lot more information on what's presented in this presentation is in that literature review.
Yes, so we are trying to present a 100-page report, David, would you say? Plus, in literally just about 30 or 40 slides. And in fact, even last week, we cut out quite a bit of slides to match the time. So keep that in mind. There's a lot more information there. This is just a summary. Okay, I've got to push on. Now, let's go with the basis. And I'm assuming most people are comfortable with about density testing. You've done a bit of that. But what we find is that a lot of things get mixed up in our standards and of why we do what we do. And we have density as one of the parameters, and they're embedded in that specification, whether it's a main road standard, a local standard, whatever. You might see about lift thicknesses and moisture contents as part of that standard. But we need to be careful here about what represents must do versus a recommendation. And hopefully this triangle illustrates that concept. You may see the requirement for lift thickness and moisture content in the same sentence as a requirement for density. It does not mean you give the equal weighting. There are two of them are supporting acts, as you see on the triangle there. To keep the other one intact, we are focused on density, pass, fail, based on your density ratio. The lift thickness is actually a recommendation, and so is the moisture content, and that gets confused about needing all three simultaneously. They're not in the same basket of requirement of what one must do from what is recommended you do to get the job done better. I.e., if you have a certain moisture content range, it may help the compaction and certainly get you there faster. It doesn't mean if you're a bit off, that's a failure. And there's a little subtlety there, especially with soils that are the equilibrium moisture content is far off from that OMC. Separate issues. I'm not going to go through a lot of that detail. Similarly for lift thickness, the question becomes, for instance, if one had a requirement for 250 mil loose lift thickness and achieve the required density, is that any different from when you achieve the required density and somebody put 300 mil loose lift rather than 250 and still achieve the density? Is that a failure? And you start to see now where the focus needs to be rather than the others would help you achieve that density required, but they are not necessarily pass and fails. And we need to be careful there about putting all of them in the same line or in the same paragraph within our standards, because people can provide equal weight into all those three when two are supporting acts to the density. So I've tried to conceptualize how we look at things there. And in fact, even when we look at the density ratio, is that what we're after? No, actually we're after the reduction of air voids, which is the top of that other triangle there. So having summarized what we are trying to achieve for compaction, we might say compaction air voids leads to density ratio, and we are supporting acts with moisture ratio, which could be climate dependent. In fact, it is. Your OMC is close to the EMC, which is more important, only for certain levels of rainfall, somewhere between 500 to 1,000 mils, which just happened to be the rainfall that Proctor had in California when he came up with his test, coincidentally, but doesn't apply to most of Australia. So we need to be careful there. In very wet climates or very arid climates, a different equation can develop of what is required. It's similar for layer thickness, which can be equipment dependent. One cannot judge layer thickness by using a 100-kilogram plate compactor versus a 20-ton roller. Obviously, a different thickness should apply, but yet that doesn't often become a considered part. We need to be careful there. So again, having the supporting acts, and we have our density ratio, our focus. Is that our focus? And the answer is no. Actually, there's a relationship there. We assume if we get the correct density ratio, that we have the correct modulus, strength, or permeability as three of key parameters of the part of design. There is not a direct relationship, and I'll just illustrate that shortly. So pushing on, let's just take a step back, history, not history for history's sake, because it is important we do understand a bit of history and give acknowledgement to the great forefathers, etc. But in fact, by understanding that historical perspective, we can appreciate why we do what we do. It's not often we make a forward step as well, so we just need to be careful that we aren't crossing the optimal line, so to speak. Okay? So let's just take a step back in the 1960s when the Highway Research Board, as it was called then, the American, now it's called Transport Research Board, back in 1960. Typically, if you read any of those papers, typical output of 100 cubic meters per hour, and a 10-ton roller was a, you were king of the roost, so to speak. By the time we reached 1980, that was 15-ton was probably it, and above 2000, the 21st century, we operate in 20-ton rollers, 25-ton rollers are not, that's pretty normal for the large jobs. But yet when we look on the QA side of it, where 200 mil lift thickness was appropriate for a certain type of roller and a certain condition or production rate, we still use it, even though there are a lot of other factors changing. So it begs the question, should we be making a change as well, a comparable change? And are we able to QA it in terms of either lift thicknesses or even the parameters we are looking at? So let's just move forward on that concept. And I'll give you a bit of history. You'll see, obviously, this is a scanned from the papers back in the 1967 Highway Research Board. You can check that reference for yourself, but you can sort of see how they were thinking back in the day, so to speak, where wet density, the one in blue, and the dry density, it had a very low variation. They call it range over average. Now we'd have to use the coefficient of variation, but let's just go run with what they have, which is not dissimilar. It had the smallest range as compared to the CBRs or the plate loads, which are very huge numbers. So that precision, underline that word, remember that word, I'm going to repeat it. Precision was a very important considered factor. There's a big difference between precision and accuracy. You need to understand that. They are not the same. So precision is what was a defining factor in descendancy in the forefathers, so to speak, who brought this to our understanding and how we should QA things. It had a very good precision in terms of repeatability, reproducibility. Those are the factors we are talking about here. Now look at the table 3, which considered combining factors instead of, because these are the considerations that do help us to understand density or improvement from compacted soil, and moisture content, lift thickness, soil type, compactive effort, and compaction equipment. Now, when we look at combining some of these things, such as, for instance, compactive effort, TC, we see none of them are represented there, none of the tests. And that's because the variation became very large. And what we circle in that little blue, I've tried to highlight the better ones. And what we see that density actually only gets up to number 3 for soil type and compaction equipment, but it doesn't reflect things like compactive effort or the actual other factors, which are lift thicknesses, etc. So you start to see, actually, when you start to combine factors of, we need to really understand all those contributing factors, it doesn't get up. It didn't get up as to something that we would want. But yet, it was the one that was focused on, because it had, going back up to table 2, it had a very repeatable value. So that's, I guess, a key summary of the history of it. And I'll leave it at that, so hopefully you understand precision, why it's there, and that's the key factor moving forward. Now, I'm just grabbing something out of BOMAG's 2001. I'll have to emphasize here, I do not have any shares in BOMAG. I do not have any interest in any of the equipment we presented. It's just, this is freely available in the net. So I don't have any bias, and it's just openly picking a random equipment, which could pick for any of these. You'll see that, in fact, by the time we reach, say, 13 to 16 ton, gravels and sands would be 0.5 to 0.8 meters lift height compaction. Now, that's significantly different from the 200 or 300 mils, which are achievable. If we go to the top row where it says 7 to 9, we'd see 300 to 400 mils for that, or 200 to 300 mils for mixed soil, or 1500 to 200. So in fact, the top column of that, those top 4 in that top row, actually represents the, shall we say, the 1960s thinking, 50 years ago. So it actually is very comparable to why 200 or 300 mil lift thickness would match that equipment of the day. So one of the considerations here is actually we are bound by that lift thickness QA process, and yet we have moved forward, and that's certainly one of the considerations. So let's just introduce one other concept through this time history part of it, of where we started with standard Proctor back in the 1930s. In the 1940s, there was another QA system, which was the modified compaction test by the US Corps of Engineers, because they were using heavier equipment, which was 10 tons, by the way. And then by the 1970s, it moved to 20 tons, and of course, we do 25 tons by the 2000s. And if you look at the red vibratory rollers, important to understand that a 20-ton can actually induce the equivalent of a 35, 40 tons of impact force when you're into vibratory mode, depending on the amplitude. So we should not just judge it by the static weight, but the actually compactive force is probably much more meaningful when you're into vibratory rollers. Separate consideration, but the other consideration is about the modified. You notice in the 1970s, when the weight doubled, it wasn't a Rev 2 or Rev 3, and we haven't moved to Rev 5, Rev 6, or iPhone 10, or whatever it is you want to call it. We all like the latest and greatest. So for those believers who think modified is the latest and greatest, well, I think you're a bit out of date, because that's 1940s stuff. It cannot be the latest and greatest. So don't think because modified is more up to date that it's current. There's a difference between more up to date, 1940s, to being current. So it actually doesn't represent a higher compaction level. It's simply a different reference measurement, which did not get modified to Rev 2, Rev 3, or whatever revision, because it was realized it actually wasn't changing the level of compaction. It was just introducing a different level, a type of measurement, you might say, a different unit of measurement. I think there's a comment from somebody.
Yeah. So, Bert, so you mentioned that the standard, and then later on we move on to the modified compaction. Is there a reason why we haven't progressed further?
Well, the reason is actually sorry, I thought it was self-evident, but it didn't progress because what happens? You start to have different units of measurement. For those who are involved, you'll see that it's not like a direct translation where you could say 95% modified with 100% standard. No, you may hear that. That may apply for some soils, but a different soil will have a different conversion. And so it actually complicated life in a different way. And of course, it costs more, it takes more. And for anyone who is into lab testing, you'll know it has a lot more muscle ache, besides so much more effort. You double the requirement of how much soil you require. It takes more effort, more cost. And have you had an added benefit? The answer was no. And so it actually didn't try to do a modified, or modified, which is where we should be if it was relevant. But back in the 1970s, it was realized that, well, the original reason for the 1940s modification didn't actually hold because it was just a different unit. You didn't change the level of compaction in the field. You simply introduced another unit of measurement. That's the point that's being made here. Okay, so we will push on. Okay, so having done that history, I hope I do have to move fairly quickly. Let's touch on a bit of density and CVR testing basics. Okay, are we close enough? No, we are missing the target. And when you see that ring and we are missing the target, that's about accuracy. That's different from precision. Remember, I mentioned about one is a very precise measurement. Density is very good at it. Are we hitting the target of accuracy? That's a separate question, and we need to be careful here about how we translate that. So hopefully that cartoon that is left gives you an idea where we are heading. Okay, a bit of history here, a bit of summary of the density testing, and thanks to Mick Morrison from Morrison Geotech who gave me some background data, and I just made it a little sexier, you might say, in terms of a nice diagram. But basically, this is the data of how long one takes to do something. 20 to 30 minutes depends on the size of sand replacement you're doing. Yes, you can report it 15 minutes, and obviously these are for the people who have done fine art. It doesn't consider overhead time of trying to prepare your sand container or your equipment and your travel time. This is just simply the minimum time required to do things. and assuming you don't have to wait and have inductions, etc., etc. But in the background to that, in the lower part of it, you have got to take some samples for your MDD and the minimum curing time. That middle one is a killer. It's not only a killer, it's a murderer. Should be charged with, yeah, with a lot of things. Because it's what kills a project, because it means there's a long wait time if you were to conform to Australian standards and do that. Then after you cure it, then you do your MDD, which may take 50 minutes. So if we look at that, what we see, it may take 1 3/4 hours roughly in total time to do the test. Again, excluding overtime, overhead time. However, 3 to 12 days. My gosh, people ask for things after 1 day or 2 days. That's not acceptable in this current push for time delivery. So, understandably, the average contractors keep on pushing dirt up, you know, and assume they have done a good job because they think they have done a good job. Even the QA may lag it a lot of times. So that's where we're at, or state of practice. And if we think about that curing time, let me just step you through what is required for the main road standard, that's called Q113A for CBR, which is where you have to prepare a sample, no different from the compaction. There's the RMS T132, which is to the far right, and the Australian standard. And there is a subtle difference between all three, but basically at least we have a standard that we can work towards, assuming NATA registration and all this sort of thing, that people are doing it similarly. And yet, we come to the question about repeatability and reproducibility, etc. The CBR is notorious for not being repeatable and reproducible. Just keep that in mind. In fact, Rawlings, I think, in an Australian Geomechanics Journal paper back in 2014, showed that when he sent out to labs across Australia, to 50 different labs, all across Australia, what he found is that less than 60% of results were even within plus or minus 30% of the CBR values. Think about it. If you have a CBR of 10%, pick any number between 13 and 7, and at least 40% of results will be outside of that range. Now, that's not good reproducibility and repeatability, and it all comes down to some extent, or a lot of it is that curing time there, and in fact, that sizing. I'll just touch on that curing time with the next slide, and I'll come to the sizing in the slide after. So if we do not do that curing time, this is an illustration of what could happen. If you only cure it for 1 day versus the 7 days or 4 days plus as required, you can have a shift of density by 10% plus, as you notice. Moisture content would shift by another 2 or 3%. So it's essential that we keep that curing time, and it is all part of the delay in the reporting phase of trying to find that MDD to get our density ratio. So very, very important, as you notice, this is an illustration. If you don't cure it, you can't fast track it. You will get a different result. Now we come to part of the equation is about the use of the size required, which is required by all these different standards, including the Australian standard. But as you notice, Queensland Main Road is treated slightly differently from RMS, which has a slight variation of treatment to the Australian standard, with that percentage crossing the 19 mils. And remember I said 22% of results I surveyed actually didn't conform to either how you should use it or how you should correct for density. And this is an illustration of what happens, and a colleague here, Dave Lacey, and Dave Marks from Queensland Main Roads, for when we looked at some results for C2C, that's Koroy to Curra, that's up north in Sunshine Coast. But anyway, the way there was generally a residual salt profile XW rock. What happens when you use a soaked CBR? You literally saturate at a certain value. No pun intended, it's a soaked CBR. But you reach a value which plateaus, and you'd think if you have a rock, it should be a better CBR. Well, it doesn't matter how good the rock is, and whether you're using a rock breaker to get a rock out, you are going to be stuck with a CBR. Imagine that. You have a material which you're having trouble to excavate, and you have a low CBR. That's because the test gets rid of this arguably the strong material, the 19% above the 19 mils. So when we are in residual soil, which has a lot of stony bits, the top one shows what you should be getting and what we tested in the field, while the other line shows what we end up getting in lab. Arguably, one may say it's a soak value, but when you come to material with a high stone, soak doesn't make too much of a difference when you have a lot of gravels and high stone content. Whether you wet it or don't wet it, for that high percentage, it's not going to be significantly different. Yet it is significantly different. So we are not availing ourselves of the strength of the material in situ, and in fact, the lab result is holding us back. And by changing CBR of 2 or 3% for sometimes we could be talking about $1 million plus of pavement per kilometer per lane.
So we are throwing away the best part of the stone structures, eh?
That's right.
And not considering whatsoever.
We're being gullible to believe that's the maximum value in a lab. That's a lab model. Keep the word model in mind. It's not reality. They have modeled it in the lab to what the best or the worst case condition is supposedly, but we have thrown away the material that exists. We're not going to do that on site during construction.
Just to go one step further as well, so Bert earlier showed that we work out a design modulus from a soak CBR, from a CBR value, and apply a single multiplier, whereas what you're seeing here in this slide, in this graph, shows that it's not a single multiplier at all. The divergence of the graph shows that there would be a expected divergence of a linear relationship as well. So if you're just multiplying the CBR by 10, for example, even you would never replicate the full range of the modulus or the stiffness parameters you're seeing in that upper line on that graph.
Okay, so you see our problem with CBR. Some while ago I made a presentation about CBR, and I called it the California Baronosaurus Rex. It's a dinosaur that lives beyond its time, but nevertheless, that's what we have. Let's move on. Okay, so any questions so far, Rosemary, that that could be present?
Thank you. We've just had 2 comments. Mick, so interesting that you're stressing the importance of adhering to curing time, and Mick made a comment, not many, if any, labs will adhere to curing times for comps. So do you think that might change now they've heard your story?
I hope, but the answer is no. You had a colleague long ago, which there's a difference between reality and what we aspire to, and we've got to make the difference too. There's something like commercial or time push or project management push. And I remember one colleague in a lab, he says, you engineers, you seem to not understand some of the basics, and this was a testing person, says, do you know how long a 4-day soak CBR takes? And I said, yeah, minimum 4 days. He said, yes. So why do people want it the day after? It's called a 4-day soak CBR, for goodness sake. So when engineers don't understand those basics, I live in hope. But no, the standard says it has to be done and it should be adhered to. And if people are not doing the right thing, they are not registered. We expect people to do the right things, but no, sometimes the ideal of isn't always adhering to, and I'm very uneasy. I do get results in record time, and I'm uneasy about those results, and people should always request results when they get it too quickly. So Mick, thanks for that. People should be doing it, but the lab, or at least advising that they need extra money to possibly do a correction factor, things like that, but it's not happening as a standard across industry. We need to understand the reality of results, if it's representative or if we should be using it. So, okay, I'll just leave it at that one question for now, and I will push on.
Beautiful, thank you.
Okay, I will take another question as we go along, Rosemary, but I'll just try to keep a bit of pace here. So what we are trying to do, obviously, is to make that shift to where we should be rather than where the target that we are hitting. With good precision, by the way, but whether we are hitting the accuracy. So let's talk about some alternative testing equipment. And the literature survey showed that these are some of the equipment which we'll illustrate shortly, of whether it was Pandas or LFWDs, the different brand names mentioned, or borehole shear tests at BHSC, where they should be. And I'll give you a little, the next slide will show how we receive those percentages, but what you will see is they are significantly above the nuclear density and sand replacement in terms of the percentages, meaning that it should be higher in usage, but it is not, and that's because we are locked into our practice of density. So while density has served us well, is it now keeping us back from using other technology, by the way, which has been around for at least 20 years, so it's not current. It's been around for a while, it's been well established. Germany, for instance, uses the light falling wave deflectometer without having to use densities and other things. So there are places that have moved away from those things. And DCP, which is much valued, I'm saying that it's good, but it doesn't have the resolution required, certainly, in some cases, and yet you notice 58%, and yet it's a much used strength for assessment as well. So what we are trying to do in this research is to get those greens and those ones low up to provide confidence that we should be using it.
Sorry, just taking a step back. We're trying to evaluate the use of largely modulus tools meant to directly measure modulus for QA of materials rather than relying on density, like we were talking about before.
Yes,
that's the overall aim of this.
That's right, and that's a different unit of measurement, which may have some people uncomfortable. These are the aspects under which we came up with that. Now, we can argue about whether we should use these percentages and whether principal costs may govern. That could have gone higher, but you'll find that the percentages that we have would have only changed by a minor amount, and it would not have changed the base consideration of we need to consider other equipment outside of density and our nuclear gauge. So that's subject to discussion in those rankings, but let's move on. That was certainly the basis of how that literature survey was completed last year. So we have traditional versus 21st century, and keep in mind we have been in the 21st century for 20 years. So this is what we're doing is not actually new, it's just simply trying to bring us into the year 2000. But the issues with some of these is they're not standardized, at least with the density, CBRs, DCPs. We have a standard in place, and there are a lack of standards with some of these new equipment, or rather they are driven by the equipment manufacturers themselves. So that's possibly part of it. And I've mentioned that models and strength, while not considered 50 years ago, and I showed you that reference paper, how it was considered very good, but it did not have the technology back in the 1960s. That's the reason why the technology wasn't there. Now we have the technology, it is open for reconsideration. We need to constantly reevaluate, are we in the best practice mode? Accepting that we need to also consider standards. So what we've done is evaluate, these are a range of equipment. They can be others added, but it gives you a flavor of some of those that we considered, or we try to consider, and the base ones which are in green, which are the reference tests, you might say, for CBRs or density testing. And we do also plate load and bent beam, typically as current standard practice, not as often, but we do those. And the ones at the bottom, which is available quality control technology, is where we are trying to focus on some of these technologies. How reliable are they? How accurate are they? And that's what we are trying to do. There is something, intelligent compaction, which is not part of this talk. That's contractor driven. And there was a talk.
There's a workshop in early May.
A workshop here back in May. But that's contractor driven. And it's saying that, do we accept the word of the contractor? Obviously not. So we can focus on the others where we can do our own independent measurements. It doesn't detract from the fact that intelligent compaction is a very, very useful tool as well moving forward. Okay, and then even though we have clever impact hammers or non-modulus measurement, you can convert as well through an equation. Much better than, of course, some of the CBR, some modulus conversion, or a density to modulus inference, which is quite different. And in so doing, we have correlations. Keep in mind, there's always scatter of results. And when we correlate something, we are trying to reference back to what we are accustomed to, such as density or CBRs. We need to be careful there about what that correlation does mean. And I will illustrate a very busy slide here. I'm going to pick up the pace here, but I would like to spend a lot of time on this, but I can't. What I'm illustrating here is something that was done a couple of years ago of trying to understand what is called type 1 and type 2 errors on the bottom there, meaning that if it's poor, we fail it. If it's good, we accept it. And that is how it should be. But there's what is called type 1 and type 2 error, where unfortunately good results get failed and bad results get passed in our equation. And there is what is called a 10% balance risk as part of usually most standards. That's all I'm going to say on that. But let's look at now some results of plate load testing versus dry density, which is a reference result. And we'll see there's a fair scatter. But what we'll also notice, there was some good modulus results which failed and for the plate load. But even more so in the light falling wave deflectometer, there were results which were modulus of 80 MPa. Those are very good results, but they were going to fail. But vice versa, there was results which were poor, i.e. 20, 30 MPa, which should fail, but yet pass according to density. So we're seeing different tests were given us. When we try to correlate things, it's not a one-to-one relationship. We need to be careful of what that correlation means. And if we look at above on the right now, this was for with a pad foot roller, we saw that there was a balanced type 1 and type 2 error. And then when we look at the other one with the smooth drum, it was an imbalance. So in other words, depending on whether you use a pad foot or smooth drum roller, you could actually have a different inference of what was good, what's called type 1 and type 2 errors. So we just need to be careful on correlating something to the past. A point I'm trying to make here through this, because legacy issues may hinder proper use and benefits. I was in the UK last year, went to the grocery to get some milk. And then I saw, how does one get a 500 mil? No, you can't. You get 560 mil. That's crazy, isn't it? Because that's not getting the benefit of a metric unit. If you say you want a 568 mil, they're locked into a legacy issue of calling it a 1 pint or 2.27 liters. I mean, who goes to a grocery and gets 2.27 liters? I mean, for heaven's sake, they haven't. If that's what you think metric is all about, you haven't moved on and you're stuck in a legacy issue here on metrication. So hopefully you understand my point about correlation and holding on to something for the past. We could actually hinder ourselves from moving forward, because this clearly wasn't moving forward, even though this is a metric country. So I'm just illustrating a little thing here, but we just hopefully point about correlations is understood. Okay, we need to move forward on tests and aims, and these were some of the tests that were considered. I'm gonna just go through this. The probability density test, and 12 weeks later, we were still waiting results. I'm proud to say that we got a result last.
It's been 6 now, so we're analysing the data.
We are analysing data. We got it last week. Hooray, hooray! I can jump up and down. But anyway, but it shows how long some things can take. Admittedly, they were trying to be make sure we had all the information, because we are trying to do these things on live projects. Some of these equipment.
And as a research project, we were probably not their highest priority.
That's right.
To be fair.
Yeah, we are not the priority. Yeah. That's right. So that's clear. We were just piggybacking on live projects, and yeah, so that's how long it took. So that's a reference or correlation. We want to correlate things back to density and also the plate load tests. Consider that to be the gold standards for all the things. The ones in yellow shows we intended to use the equipment, but for various reasons we couldn't get it in time or at the time we wanted, so we did not use those. But we did use various other equipment here, such as the 2 different LFWDs, a Zone and a Primut. We did try to get an Olsen, but it wasn't available. We used a Panda, a GeoGauge, Clegg hammers, plate load test as well, which is not shown here. So these are some of the equipment, and Jeffrey will give you a quick summary on that shortly. But part of the equation is understanding what is the zone of influence. Density measures to within 200 or 300 mils, and so is nuclear gauge. But these other instruments are actually measuring a different zone. So the correlation is not going to be one-to-one for this very reason as well. Each equipment has a different reference zone of its influence depth. Certainly the DCPs and the Pandas can go to whatever depth if we can get it through. But the surface-based equipment, is measuring something with a different zone of influence. So hold that thought in your mind while Jeffrey runs through quickly some of these details of the equipment.
Okay, thanks, Bert. I'll give Bert a little bit break.
Yes, I'm having my drink of water.
So here's some slide about the different equipment that Bert just talked about, and yeah, so it brings everyone in the audience to the same place. So I'll do this rather quickly. So DCP, right? Dynamic cone spectrometer, as mentioned, there's high utilizations in the industry, and it's a low-cost penetration tool, and I think one of the reasons is because of the simplicity and the low cost. So and again, it's an index testing to correlate with CBR and other material parameters. As shown in the slide, there are a couple of standards, and they have slightly different drop weight as well as the cone tip angle. So that's that. And we got the Panda, which to me is a electronic version of DCP. So when rather than putting a drop weight, a operator actually strike the hammer on the plate, and after each blow, it measures the penetration of the rod, how much advanced the energy imparted, as well as the cone tip resistance. Similar to DCP is also an index testing, and I have a trial of that in the field. The hammer in the striking place not that easy to hit on my book, but it's just me. And then we got the plate load test, which a static plate load test has been around for a long time, as presented in earlier slide, and it's often being used as a reference test to measure the deformation and modulus. There are quite a few applicable standards, like ASTM and the German standards as well. And based on the result, from the loading and unloading cycle, we can get quite a number of material parameters as listed in the slide here. And then we got the light FWD. There's actually, I think two broad categorizations of it. There's some version that has a low cell built into it. There's others that don't, and as a result, there's two ASTM standard describing these two categories. I guess the reason that if you have a low cell, then you don't have to assume the load that's being dropped on the.
So one of these LFWDs, in the slide here, the premium model, but the ones that equipped with a load cell, you can vary the drop height to vary the test stress being imparted, whereas the ones that don't have a load cell generally have a fixed drop height that has been calibrated to a known stress. One of the biggest issues with LFWD is the different manufacturers and the different locations of the geophone and the presence of a load cell, or the way they measure the deflection means the modulus parameter provided, which is a number after you drop it onto the ground, is different for each brand or each manufacturer, which has then implications and problems when you write a specification stating you need to achieve a modulus threshold for passing, and then a different brand is utilised in the field. So you just need to specify that when you're using it in the field.
Thanks, David. And I get asked a lot, is FWD the same as the light FWD? And the answer is no. Even though both of them use a drop weight, the way I see it, the pressure that is imparted on the ground, and the number of sensors and other things, the two equipment have their special place. I'll just leave it at that. And we got the click hammer. It's really a simple device. Again, we got Australian standard and a ASTM standard for that. So by dropping the height at different, the weight at different set height, you basically measure the deceleration rate from a high precision accelerometer, and then from that you get the click impact value, and there's some correlation to convert to modulus as well. And then lastly, there's the geo gauge. So it's basically a surface-based plate stress test. So in other words, when you place the device on top of the soil, click of a button, there's a 25 program steady state frequency. So basically, it's sweeping through a range of frequencies, and then the stiffness is measured based on the average of those 25 frequencies. And if you want to learn more about that, ASTM, and there are tons of applications that you can find.
So all these equipment are fully detailed in the literature review we completed last year, and would be available for download off the NACOE website.
Yes. So go to the website again.
Okay, so what we did as a quick summary, because we will present the results in the next webinar, but you'll see the equipment's being used on a live site here. The far left, you see the LFWD and the pan, somebody using the panda in the background. The plate load test is being done with the ruler in the far background, and in the middle you see the geogauge and the plate load test, and what do you call a lot of equipment together? Is there such a word? A flock of equipment?
The group photo.
A group photo, right. So here we have different equipment being done next to the density testing, whether it's the LFWD, Clegg hammer, or plate load. So you get this is what was done in the past few months. We will present the results of that shortly. And this is how we are processing the results, trying to compare, in this case, the Clegg hammer with different drop heights and the coefficient of variation spread. In this case, the far left is 32%, or coefficient of variation 25%. That's coefficient of variation, by the way, standard deviation divided by mean. That gives you an idea of the spread of results. That's all to do with precision. How is it repeatable and reproducible? That's not accuracy yet. That is a different factor. So we are trying to understand the precision, because density has a good precision, and trying to make that comparison. So I'll jump straight to the last technical slide, and this provides a summary. It's still a work in progress, and things may move up one or two places. But if we go to the far right, based on time only, we can do an LFWD zone in 1/10 the time as a sand replacement. That's not reported time, which will take longer for the sand replacement. A geogauge 1.3T, and what you'll notice is basically most of these tests can be done in quarter of the time you can do the sand replacement. So certainly in terms of time, there's a reason why we should do it or look into it. In terms of precision, yes, remember the sand replacement nuclear density is one of the best precisions. Are the others as precise? The answer is no, meaning that we are grading downwards, and the plate load test, which arguably is another gold standard, is actually not that precise. Very variable, very accurate, but not very precise. And we'll come to that discussion quite separately. Now, the amount of data you're acquiring, actually the sand replacement nuclear density provides the least data as compared to the plate load, which provides the maximum data. So it depends on which criteria we are chasing. We could come up with a different reason for using some of these tests. And in terms of accuracy, as I said, we waited a long while. We have the results now. We are trying to cross-correlate, which has its own issue, with density. But overall, using, again, the plate load test as the #1 accuracy, even though it's the lowest precision, we start to see a different range of how these things are performing. And the DCP, one of our most treasured tools, the 0 to 100, very bad in accuracy. You shouldn't have to use it at all. It's only accuracy improves when you reach the 100, 200 mils, and you'll see how the other equipment are panning out. So without going through the nuts and bolts of how we arrive there, I've just tried to give you a summary, because the nuts and bolts will follow in the next seminar in the next few months, which Jeffrey might confirm that. And so I guess as a quick overview of, sometimes we need to be careful of what we are looking at. Are we looking at the bird, so to speak, or the bird next to the holes in the rock? Or maybe we should be looking at the boulder, the holes in the boulder. Or maybe we should be seeing something else. Just be careful on what density means, because are we really after density? And the answer is no. Of course, it's the density ratio, but are we really after that? No, it's a reduced void ratio. Are we really after that? No, actually, we have to strengthen modulus. So people could get confused about density being the end game. It's not. It's a means to an end, and we need to sometimes understand that, because we have the technology currently to get to the end game without the intermediates in between. So I'll leave that with you, and any more questions or any more comments from any of the other members. We only have a couple minutes or two.
Thank you.
Rosemary,
Yes,
any questions?
thanks. We've got comments from Zara, Nick, Rick, Andrew, Joe, Eric, Davin, and Amur. So what we'll do, I'll pop them into an email, and you can respond to them, and we'll send them out when we send the recording link. Amir says, thanks for the session. Where do you see the role of geophysics, in particular electromagnetic waves, in the future of road construction quality control?
Dave, you have a degree in geophysics. You tell us.
Yeah, we don't. So
Geophysics would be quite useful as long as it's got the resolution to pick up the changes in modulus. So geophysics, you relate straight to modulus and bypass density, and you look at the shear wave, various methods, but predominantly you look at shear wave velocities or wave velocities. As long as it's sensitive enough, and as long as you're looking for the right things, and as long as you're looking deep enough, so like the DCP, the unbound surface is going to present problems at the trafficable surface you're testing from. But if you're looking for an overall embankment compaction assessment, and that will also incorporate the benefit achieved by overlaying additional layers on top of what you've actually tested. It actually has potentially a bright future, or using as a QA at the end of your embankment construction, so you can actually assess the embankment fully, like your slide about looking at the entire rock compared to just the bird. Geophysics would have a very very strong role to play there. But again, it's just another test, takes another set of time to set up on site, another subcontractor to do. So there's a lot of other issues.
It will have an operational cost associated with it, and a higher principal cost, so to speak. Look, I guess that's an idealistic thing. I'm a more pragmatic person. I think people are more likely to consider geophysics much more black box, whether it is or isn't so. I'm just being pragmatic here, moving forward.
And you also would have to wait. So to get a really good geophysics result, we would be looking at the embankment in its entirety when it's finished, which means you wouldn't then have the opportunity to go back and rectify failures as you would progress them up in lifts and things like that.
You need more analytical downtime. Yeah. Okay.
Beautiful. And we've got questions from, more questions from Mick, Arun, and Mick again, and Bindu Wava and Hardy. So thank you so much for all those questions that have just come in towards the end. And thank you so much, Jeffrey, Bert, and David. Do you have any final comments? And please know that we'll get to those questions through email. Over to you, Bert and David.
Yeah, Rosemary, thanks a lot, and thanks for everyone participating. My closing comment is, as we know, with all this correlation on geomechanics material, the material type is crucial, and so if there's contractors, design consultant out there that would like to open up their projects for us to test, I mean, you got my emails, and you know where to find me. So yeah, make sure you call.
Yeah, thanks for that, Jeffrey, because a lot of people hesitant thinking we are QAing them. We are not. We're just running parallel independent testing, which doesn't affect your day-to-day process, so to speak.
Yeah, absolutely. So we're not auditing anyone. We're really just trying to build a database so we can assess the reliability and the suitability for in a new test to take the place of what a lot of people have issues with. We're not the only ones, obviously.
That's right. So the technology is there. The only question is when we implement it. Over and out for me.
Yep.
Thank you. And Harry says thank you all. And Eric says great project. And I've just cut someone off. Who else was going to speak?
No, I was going to say thanks to Arv for facilitating these webinar series. It's a really good way of disseminating some results, I think, and reaching a good audience. So
and we got a lot more interesting research project in the NACOE program. So do check, please.
Awesome. And thank you so much for organising this webinar. Appreciated from Oren from Monash Uni. Thank you, everyone. We'll close off now.
Thanks, Rosemary.
Thanks, Rosemary.